Welcome to the pod Biomanufacturing and Fermentation Technology. In this episode, we translate microbial science, process engineering, and manufacturing realities into insights that scale.
Imagine a machine so finely tuned and, working so incredibly hard that just to keep the microscopic life inside it from literally boiling itself alive, it has to pump more than 4 times its own volume in cooling water every single hour.
Yeah, it's wild.
It really is. Welcome to the Deep Dive. Today we are looking at a highly detailed engineering document titled Ideal Characteristics of a Bioreactor or Fermenter. And our mission for this deep dive is to demystify the incredible hidden infrastructure behind modern biology. We're going to look at how we actually scale up the production of life-saving medicines, advanced materials, and next-generation foods.
Because the reality is the bridge between a brilliant biological discovery and a product actually sitting on a shelf, it isn't just more biology, it's hardcore, unyielding engineering.
Right. And for you listening, think of this as your shortcut to understanding the mechanical heartbeat of the entire bioeconomy. Even if you aren't an engineer, understanding these physical vessels is the absolute key to understanding how a breakthrough in a tiny petri dish becomes a real-world reality.
Exactly. You can't just, dump genetically modified yeast into a giant bucket, stir it with a wooden spoon, and expect a miracle.
Okay, let's unpack this. What is the actual fundamental difference between a simple vat, like a giant industrial soup pot, and a fit-for-purpose bioreactor?
Well, a simple vat is passive. It's really just a container meant to hold a volume of liquid. A bioreactor, on the other hand, is a dynamic, highly responsive life support system.
Okay, so it's actively doing something.
Very active. It is a machine designed to continuously balance physics, chemistry, and biology in real time. It doesn't just hold a reaction, it aggressively manages a highly volatile environment so that a specific, delicate organism can thrive at a massive commercial scale.
That brings up a critical starting point from the source material. Before we can even sketch out the blueprints for this machine, we have to know exactly who is going to be living inside, right?
Yeah, that's step one.
Because the entire design of the vessel is completely dictated by the biological process requirement. Form follows function, quite literally.
Right, you never build a generic tank and then ask, what should we brew in here? The biological organism is the architect.
It calls the shots.
Exactly. Its metabolism, its physical toughness, its oxygen appetite. Those traits dictate every single piece of steel and every motor you install.
Reading through the descriptions of these different organisms, it sounds like the difference between housing a chaotic heavy metal rock band versus a delicate symphony orchestra.
Oh, I love that. That analogy captures the engineering divide perfectly.
Yeah.
The forces at play are completely at odds with one another.
So let's look at the rock band first. The source talks about microbial high cell density fermentation.
Right.
We're talking about bacteria or yeast. And they are aggressive, they consume resources furiously, and they multiply at staggering rates. So the mechanical design for that requires a very specific brute force approach, right?
Extremely brute force. A microbial reactor requires violent aeration. These organisms are consuming oxygen so fast that if you stop pumping air for even a minute, the culture starts to suffocate.
Just 1 minute.
Yeah, it's that fast. To support that oxygen transfer, you need massive, powerful impellers just churning the liquid. And because they are metabolizing sugars so aggressively, they generate a stunning amount of heat.
Wow.
So your heat removal capacity has to be immense.
But then we look at the symphony orchestra, right? Mammalian cell systems. These are the cells used to make complex things like monoclonal antibodies.
Yes.
And mammalian cells don't have the tough, rigid cell walls that bacteria or yeast possess. They are incredibly shear sensitive.
And shear, in this context, refers to the physical stress caused by the fluid moving against the cells.
Okay.
If you dropped those delicate mammalian cells into the microbial reactor we just described, the physical force of those giant impellers ripping through the liquid would literally tear the cell membranes apart.
So the symphony orchestra gets completely crushed in the mosh pit.
Exactly the visual. So for mammalian cells, you need an alternative structural configuration. You might still use a stirred tank, but the internal physics are completely different.
How?
Well, you use low shear impellers shaped to create gentle, sweeping fluid movements. You need incredibly tight, delicate control over dissolved oxygen rather than just, blasting it with air. And you need strict control over any particulates.
So the internal geometry is paramount. The source points out that while stirred tank designs are favored for those aerobic microbial processes, the internal physics have to be tuned to specific performance indicators.
Right.
It mentions 3 vital ones. There's mixing time, the shear profile, and something called Kala.
Yeah, mixing time is fairly intuitive. It's really just a measure of how long it takes for a drop of nutrient to become perfectly evenly distributed throughout the entire tank.
Okay, that makes sense.
And the shear profile is the map of physical stress we just talked about. But kalakla is often the single most critical bottleneck in biomanufacturing.
The text calls it the volumetric mass transfer coefficient, which I have to say sounds incredibly dry.
Yeah.
Help me visualize what Kala actually represents in the tank.
Think of it as an efficiency score for oxygen delivery. When you pump air into the bottom of a tank, it forms bubbles, obviously. But the cells can't eat a bubble.
Right.
They can only consume oxygen that has been physically dissolved into the liquid media. So Kala measures how well your reactor forces that oxygen to cross the barrier from the inside of the air bubble out into the liquid.
Oh, I see. So it's like trying to dissolve a mountain of sugar into iced tea versus hot tea. You can dump the sugar in, but getting it to actually absorb into the liquid is a physical, mechanical talent.
That's a great way to think about it. And as a tank gets larger, say, moving from a laboratory bench to a huge commercial facility maintaining a high Kala becomes an absolute nightmare.
Which is a perfect segue into the next huge hurdle outlined in the text.
Yeah.
We know who lives in the tank. We know if they are a rock band or an orchestra. Now, how do we keep them alive at scale?
Right, the utility.
Yeah, we have to look at their appetite and their energy output. And honestly, looking at the engineering specs for the utilities, like the air compressors, the cooling systems,
Yeah.
I have to push back a little on the traditional engineering logic here.
Really? How so?
Well, in a standard factory, if you need a cooling system for a 1,000-liter tank, you go to an industrial catalog, you look up the average cooling requirement for a vessel that size, and you just buy an off-the-shelf chiller. But the source seems to suggest that doing that in biomanufacturing is a recipe for disaster. Why can't we just use standard averages?
What's fascinating here is that relying on an average load is the #1 way to completely crash a biological process.
Seriously.
Absolutely. The source establishes a golden rule. You must size your utilities from the process duty, specifically calculating for the absolute maximum load at peak growth.
Peak growth. Not the average taken over, like a 2-week run.
Because biological growth is exponential, not linear. For the first 3 days of a batch, the cells might be adjusting. They barely use any oxygen. They barely generate any heat. An off-the-shelf chiller handles it effortlessly.
Right, they're just getting comfortable.
But suddenly, at hour 72, they hit logarithmic growth. The population explodes. The oxygen demand spikes vertically. If your systems are sized for the average, they will be violently overwhelmed during that peak. The cells either suffocate or they literally cook in their own metabolic heat.
That is wild.
Yeah.
I want to dig into the actual math the source provides to prove this because it honestly looks a bit like rocket science. Let's start with oxygen demand. It lists this equation, OTR equals KLA times C star minus C. In plain English, what are we calculating here?
Okay, so OTR is your oxygen transfer rate. That formula is just calculating the total amount of oxygen you are successfully driving to the liquid over time.
Okay.
And C star minus C is the concentration gradient. Basically, it's how hungry the liquid is for oxygen at that specific moment.
Okay, so applying that to a real scenario from the text. They use a 1,000-liter working volume tank. And they say a realistic peak oxygen uptake for a dense microbial culture is 200 millimoles of oxygen per liter per hour.
Right.
When you multiply that out, the total demand is 6.4 kilograms of oxygen per hour, which to a layperson doesn't sound like a massive amount of weight.
It doesn't until you look at the mechanics of delivering it. You aren't just handing the cells a solid block of oxygen. You have to blow air into the tank, and ambient air is only about 21% oxygen.
And the transfer isn't perfect, right?
Oh, no.
I imagine a lot of that air is just going to bubble straight up to the surface and pop out the exhaust valve without ever dissolving.
A massive percentage of it, yeah. The physics of mass transfer mean that to actually get 6.4 kilograms of oxygen to dissolve into the fluid, you have to blast an unbelievably huge volume of air through the system. Often regular air simply isn't enough to meet that peak demand. The liquid just can't absorb it fast enough.
So what do? Do you just spin the blades faster?
Well, you can try increasing agitation to smash the bubbles into microscopic sizes, which increases their surface area. But eventually you hit a mechanical limit.
Right.
So you have to use advanced strategies. You might blend in pure medical-grade oxygen to enrich the air supply, or you physically pressurize the entire tank.
Oh, like a pressure cooker?
Kind of. By increasing the pressure inside the vessel, you forcefully drive more gas into the liquid solution.
It's an intense engineering tightrope. And the friction from all that mechanical effort brings us to the second utility issue, which is heat. We mentioned metabolic heat, the warmth the cells generate just by eating and dividing. But the source points out that a massive portion of the heat comes directly from the machine itself.
Think about the kinetic energy involved. You are taking a massive steel shaft with wide metal blades, and you're driving it through a thick, viscous liquid at high speeds to smash millions of air bubbles apart.
That sounds exhausting.
It generates severe mechanical heat. Add to that the heat created simply by compressing the gas to push it into the tank.
The source provides another formula here, a simplified cooling estimate. Q equals m times Cp times delta T. It's the foundational equation for thermodynamics, right?
Yes, exactly.
Basically, to figure out your cooling load, you multiply the mass of your water by its heat capacity and the allowable change in temperature.
Let's ground that in their specific example.
Right, they assume a 25 kilowatt heat load in a 1,000-liter tank. And they stipulate that the cooling water entering the jacket surrounding the tank is only allowed to warm up by 5 degrees Kelvin before it has to cycle out, just to keep the internal temperature perfectly stable.
Okay, so what's the result?
When you run that math, you need about 1.2 kilograms of water flowing through the jacket every single second.
To really visualize that, we need to convert that mass into a volume that makes sense.
I did the conversion, and it's staggering. It is roughly 4.3 cubic meters of cooling water per hour for a tank that only holds 1,000 liters of product.
It's incredible.
You are literally pumping more than 4 times the entire volume of the tank in cooling water every hour just to fight off the heat generated by the biology and the friction.
And keep in mind that math assumes a perfectly clean system. It doesn't account for safety margins or the fact that over a long run, the inside of that cooling jacket might develop mineral scale, which insulates the steel and reduces your cooling efficiency.
This perfectly illustrates why the source emphasizes the nightmare of scale-up. Taking a process that works in a 10-liter benchtop tank and moving it to a 10,000-liter commercial facility, it isn't just a matter of building a bigger cylinder.
The square cube law becomes your biggest enemy. As a tank gets larger, its total volume increases exponentially faster than its surface area.
Okay.
So a 10,000-liter tank has vastly less surface area per liter of liquid than a small benchtop tank. That means you have comparatively less jacket space to run that cooling water through.
So the heat gets trapped in the center of the liquid volume.
Yes, and mechanically, geometric similarity completely breaks down. You cannot simply maintain the same relative agitation power per volume.
Why not?
If you tried to spin a massive commercial impeller with the same proportional kinetic energy you use in a lab-scale tank, the physical torque would likely twist the solid steel agitator shaft in half.
Oh, wow. So we've got this massive steel fortress. It's spinning furiously. We're blasting it with cold water and highly pressurized air. But all of that brutal mechanical effort is completely useless if one single microscopic interloper crashes the party.
That's the terrifying part.
We have to look at the physical architecture itself, the anatomy of sterility. So what is this vessel actually made of to withstand this level of pressure and biological precision?
Well, it is built to extraordinary, highly regulated standards.
Right.
The source details the absolute requirement for ASME BPE style hygienic design. It stands for Bioprocessing equipment, and it is the global standard for purity. First, consider the metal itself. For any wetted part, meaning any surface that actually touches the biological product, the baseline material is 316L stainless steel.
The L meaning low carbon, right? To prevent corrosion around the weld seams.
Precisely. The welds have to be flawless. And you don't just, order the steel from an industrial catalog. It requires rigorous, documented material traceability.
Like a birth certificate for the steel.
Exactly. You need verified certificates proving exactly which foundry that steel came from and its exact metallurgical composition down to the fractional percentages.
Because a tiny trace impurity in the alloy could leach into the batch or cause a microscopic spot of rust where a rogue bacteria could hide.
And hiding spots are the ultimate enemy. That's why the finish of the steel is so critical. The source specifies that the interior must be electropolished or mechanically polished to an APRAL, a roughness average of less than or equal to 0.5 to 0.8 micrometers, depending on the risk level of the process.
Let's explain why that submicron number matters. Because to the naked eye, a standard stainless steel countertop looks perfectly smooth. But we aren't engineering for the human eye.
No, we're engineering for a microbe. To a bacterial cell, standard industrial steel looks like the Grand Canyon.
Wow.
It is full of microscopic valleys, jagged ridges, and deep caves. If a bacteria settles into one of those microscopic valleys, cleaning chemicals might just wash right over the top of it.
Oh, I see.
Polishing the steel down to 0.5 micrometers essentially levels the mountain range. It leaves no physical harbor for contaminants.
Which is critical for the cleaning protocols. The source explains the vessel must be built for CIP and SIP, clean in place and sterilize in place. You don't take a 10,000-liter tank apart with wrenches between batches.
Yeah, definitely not.
You run automated chemical washes through it, and then you sterilize the entire sealed system using saturated steam, hitting at least 121 degrees Celsius.
And 121 degrees is a very specific, crucial number. Simply boiling water at 100 degrees Celsius is not enough to achieve true sterilization.
Really? I thought boiling killed everything.
Not everything. Certain highly resilient bacterial endospores can survive boiling water. You have to introduce pressurized steam to reach 121 degrees to physically denature those hardy spores.
This brings up a major design danger the text highlights, something called dead legs. It sounds ominous. What exactly is a dead leg in a bioreactor?
A dead leg is any section of piping or a sensor port where fluid or steam doesn't actively flow through. Imagine a short, dead-end pipe branching off the side of the main tank.
Okay.
When you flood the main vessel with 121-degree steam, the ambient air trapped at the end of that dead-end pipe might act as an insulating cushion. The steam can't fully penetrate it.
So it creates a microscopic cold spot.
A cold spot that might only reach, say, 110 degrees. If a single spore survives in that dead leg, the moment you fill the tank with warm, rich nutrient media, that spore will wake up, wash into the main tank, multiply exponentially, and destroy a batch that might be worth millions of dollars. Easily. Designing out every single dead leg and ensuring perfect steam flow is an absolute obsession in biomanufacturing.
Here's where it gets really interesting for me. We talk so much about the 316L stainless steel. It gets all the glory. But steel doesn't bend. To connect two pipes or seal a glass viewing window, you need flexible seals. The unsung heroes of the bioreactor are the non-metallic parts.
Oh, absolutely. The elastomers and polymers, they hold the fortress together.
Yes, the gaskets, the O-rings, the valve diaphragms. The source explicitly states that these are made of highly advanced materials. We're talking about PTFE, which most people know as Teflon, or heavy-duty synthetic rubbers like EPDM, FKM, and high-grade silicone.
Right.
And the crucial takeaway here is that you cannot just use whatever standard gasket the vendor ships by default.
You absolutely cannot. The choice of elastomer has to be specifically mapped to the chemistry of your process and your cleaning cycle.
Because if your automated cleaning process uses a harsh solvent or an acid that slowly degrades standard silicone,
then over the course of 50 cleaning cycles, that silicone gasket is going to start breaking down. It will shed microscopic chemical particles, which are known in the industry as extractables and leachables, directly into your medicine or food product.
yikes.
Or worse, the seal loses its integrity entirely, microscopic gaps form, and a wild contaminant gets sucked into the tank.
Which transitions us to a harsh, unavoidable reality of manufacturing. A pristine, perfectly polished stainless steel vessel with brand new Teflon seals is only a snapshot in time. It looks magnificent on day 1. But what happens on day 100? What happens on day 500?
It's breakdown.
Exactly. We have moved from the static design of the machine to the grueling reality of continuous operation.
Yes.
And reading the life cycle section of the source, it strikes me that buying a cheap bioreactor from a discount vendor is an absolute trap.
It is an economic landmine. The capital expenditure, the upfront cost to buy the steel is only a fraction of the story.
It feels exactly like buying a high-end, exotic, luxury sports car at a massive discount, driving it home, and suddenly realizing there isn't a mechanic within 1,000 miles who knows how to fix it. And every replacement spark plug has to be custom shipped from an overseas factory.
That is the perfect way to look at it. The source emphasizes that a fermenter's design is only as strong as its service ecosystem. Maintenance cannot be an afterthought. It must be designed into the equipment from the very first blueprint.
Because in the continuous biological process, you can't just pause the cells for 3 weeks while you wait for a FedEx package.
Exactly. The high-risk components, like the mechanical seals on that furiously spinning agitator shaft, the polymer gaskets, the spargers distributing the air, the sensitive probes measuring pH and oxygen, these are the frontline troops.
They take all the damage.
They take the brunt of the heat, the pressure, and the corrosive cleaning chemicals. When a mechanical seal fails, you instantly lose the sterile boundary. The batch is dead.
And the text points out something incredibly specific about how a biomanufacturing facility has to treat these replacement parts. You can't just run to a local hardware store and grab a rubber O-ring that looks like it fits.
The regulatory agencies would shut you down immediately. Every consumable part must be a heavily qualified item. That means it needs a documented part number, a strict proactive replacement interval based on validation testing, and rigid change control records.
A paper trail for every single piece of rubber.
Because if you quietly switch the brand of an O-ring, that new rubber might have a slightly different chemical curing agent, which could leach into the batch and alter the biological product. So tracking the exact provenance of every consumable is a regulatory mandate.
This plays directly into the total cost of ownership, which the source tackles head-on. It gives a very specific context for North American deployments. It states that if a reactor cannot be serviced by local technicians, or if the spare parts cannot be obtained rapidly, the total cost of ownership skyrockets, rendering any upfront savings from a cheap purchase price totally irrelevant.
It comes down to the brutal economics of downtime. Imagine a commercial facility producing an advanced mRNA vaccine or a highly specialized biologic drug.
Okay.
A single batch inside that tank could be worth $5 or $10 million.
Wow.
If a proprietary valve diaphragm blows out and you lose the batch, that's a massive hit. But if it takes you a month to get a replacement part from an overseas vendor, you haven't just lost one batch, you've lost a month of production capacity. The machine becomes a multi-ton useless paperweight.
So the facility is forced to hold massive inventories of fast-moving consumables on site, and they have to define strict reorder points for any long-lead items. It really is a logistical war as much as an engineering one.
It's all connected. The biological organism demands the perfect environment. The utilities and the steel create that environment. And the served-as ecosystem ensures that the environment doesn't collapse on day 500.
So what does this all mean for you listening? Next time you are reading the news and you see a headline about a revolutionary new biological product, maybe it's a lab-grown meat that promises to reshape agriculture, or a custom-designed microbe engineered to eat ocean plastic, or the next generation of therapeutics. It is so easy to give all the credit to the genetic engineering.
The DNA is glamorous.
It is. But the real, unsung heroes, the actual physical bridge between a brilliant science experiment and a global commercial solution, are these meticulously engineered vessels. It's the relentless balancing of the candela, the management of massive thermodynamic loads, and the unyielding microscopic obsession with sterility that actually drags the future into reality.
If we connect this to the bigger picture, a bioreactor represents the ultimate convergence of disciplines. It is an elegant, highly aggressive intersection of microbiology, fluid dynamics, metallurgy, and thermodynamics. It is human engineering attempting to perfectly mimic, control, and scale the deeply complex conditions of life itself.
And that leaves us with a fascinating, somewhat provocative thought to ponder. Throughout this deep dive, we've talked about optimizing these rigid stainless steel tanks to support the organisms we know today. But synthetic biology is moving incredibly fast. We are designing entirely new, unprecedented organisms with completely alien metabolic needs.
Right.
What happens when we reach the absolute physical limits of 316L stainless steel and traditional stirred tank physics? As the biology gets more complex, will the bioreactors of the future even look like rigid industrial tanks at all? Or will we eventually have to engineer vessels that flex, breathe, and mimic the soft biological organs they are trying to support? Something to think about the next time you picture the manufacturing assembly line of the future. Thank you for joining us on this deep dive. Stay curious and keep exploring.
You've been listening to Biomanufacturing and Fermentation Technology with Prasad Ernala. Thank you for joining me. Until next time, keep engineering biology into reliable manufacturing.